In the next phase of our study of kinematics, we're going to learn about the SUVAT equations and where they come from. What the SUVAT equations are will also be explained. We're first going to consider the case of constant speed. But before we delve into that first example, we're going to talk a little bit more about what SUVAT equations are. What exactly is a SUVAT equation? A SUVAT equation is an equation that involves these variables: displacement, given as s, initial velocity, which is given as u, v, instantaneous velocity, a, acceleration, and t, time. The only one of these that should be new at this point is defining displacement as s. S, SUVAT, SUVAT equation. We could just as well have called these the SUVAT equations, X being pronounced sh in many languages. So what are the significance of these equations? Well, the first significance is that all the equations require that acceleration be constant. This is very, very important for these formulas. All of them work if acceleration is constant, and if acceleration isn't constant, then none of them works. The IB data booklet lists the equations, the SUVAT equations. Not all of the SUVAT equations, but the ones they consider necessary to list for you. In this lesson and throughout the course, we will learn more advanced version of all of these equations. I will teach them to you because they relate directly to HL math and calculus, and they allow for understanding kinematics with graphs. And the SUVAT equations do not lend themselves to that so easily. So these are the variables: SUVAT, significance, acceleration, must be constant. So here are the actual equations and the more advanced forms. What you can see here is this vertical arrangement is the SUVAT equations. So S equals U plus V over 2 times T. Now you'll recognize this as the average of the initial and the final velocities times time. So this is V bar T. This is the average velocity times the time. The equivalent in the more advanced form is to call displacement delta x, final velocity plus initial velocity over 2 times time. So you see they're almost identical to each other. The next equation we will not be getting into in today's lesson, but I'm going to show it to you because these are the formulas that are on the data booklet. S, the displacement, is equal to 1/2 at squared, where a is the acceleration, plus the initial speed times the time. Notice the more advanced version, delta x in place of s. The rest of this term is the same, and we've just replaced u with v0. In the more advanced version, and this is where the graphing comes into play, we can actually describe, rather than the displacement, the position being this same term, but taking into account the initial position. Taking into account the initial position allows us to make a graph of the actual position as opposed to the displacement. And it should come as no surprise that delta x equals x minus x0. So if we were to subtract x0 from this side, we would have x minus x0 over here, and that would be equal to delta x. And these two equations would be equal to each other. The last equation is what I call the combined formula, where the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. This is not at all obvious, and this will be the last of the SUVAT equations that we study. This is the more advanced version. Again, v, initial velocity, acceleration, and delta x for displacement instead of s for displacement. Simply knowing these equations will allow you to solve most kinematics problems and nearly all of them if the acceleration is constant. I will spend considerable time in deriving them and their meaning graphically in the following lessons. So let us now consider our first example. Our first SUVAT example of constant velocity. So we have a dog starting 4 meters south of the house and walks northward at 2 meters per second for 8 seconds. So we have our number line, one-dimensional motion. Here is the house, and we'll have north and south. We'll make this north positive and south negative. The dog starts 4 meters south, so the dog starts here, and this is x0, the initial position. And it walks northward in this direction at 2 meters per second for 8 seconds. So in the first second, 2 meters, 2 meters, 2 meters, 2 meters. So we can see we've got 1 second, 2 seconds, 3 seconds, 4 seconds, and we can see that they end up at a position much further north than a position of +4. So here is a motion diagram so we can understand the actual motion itself. So we can see we have an initial position that's negative, a velocity that's positive because it's moving in the positive direction. We see that the displacement is increasing at a steady rate. We see the distance is increasing and the position is also increasing at a constant rate. So the question we might ask is, where does this dog end up at the end of 8 seconds? Well, in one simple way to solve this is to do a calculation. We could take a look at the distance. The distance we know is related to the average velocity with this equation. If we arrange it, the distance then is the average velocity times the time. The average velocity is 2, and we know the time is 8, so the distance then is 16 meters. That's a simple calculation to arrive at. Now we can also take a look at this from the displacement perspective. We know that the average velocity is the change in position over the change in time. So to find the displacement, delta x, that would be equal to the average velocity times the change in time. So the displacement then would be the average velocity, which is +2, and the time is 8 seconds. So we find the displacement is 16 meters. And we know that displacement is positive. It's moving in the positive direction. So that's displacement. I want to pause our calculations now to talk a little bit about the graph. Now earlier we learned about graphs that with every graph there are three valuable bits of information that we may be able to get and how to get them. The first thing we can get off any graph is the information we can read. And we can read the axes, velocity and time. We can glean something oftentimes from the gradient, which in this case is delta v over delta t, which you may remember is the acceleration. That's not our important concern for today, but we will come back to that in a moment. Lastly is area. And you may recall that the area we get by multiplying the axes and doing a dimensional analysis. Well, we get v times t, which is equal to delta x, the displacement. So the area of this graph will give us the displacement. We can read the velocity and time, and there's this gradient delta v over delta t, which we're going to come back to in a moment. So in our situation here, we have a velocity of +2, it starts out at a velocity of positive 2, and we are told that that velocity remains the same for the entire 8 seconds. So what we see a graph of 0 slope, a horizontal line, a straight horizontal line. We notice the gradient is 0. Well, what's the gradient? The gradient is equal to the acceleration. Well, acceleration is change in speed. There's no change in speed. There's no change in velocity in this situation. So we would, of course, expect the gradient to be 0. We also learned that the area is the displacement. So the area under this curve would be given by this rectangle. So the area in this case, which gives us the quantity, the displacement, is equal to the area. So let's examine the area. It's a rectangle, so the area then of the rectangle is length times width. And the length, in this case, we might consider to be 8. In this direction 8, in this dimension 2. So 8 times 2 gives us an area of 16. Now if we did the dimensional analysis, we have 8, which is seconds, and 2, which is meters per second. And you can see the seconds cancel and we're left with meters. So the area of the rectangle also gives us 16 meters, which of course we can see agrees with the displacement. So the last question that I would like to ask is, where is the dog at the end? At t equals 8 seconds. This is the position. Well, let's consider this from our number line conceptually. We know the dog started here, and we know its displacement is positive 16. So if it moves 16 units in this direction, it's going to be 16 plus a negative 4. 16 plus a negative 4. So what we are doing in that case is we are taking the displacement and adding the initial position to find the overall position. So in other words, the position is equal to the displacement, delta x, plus the initial position. And delta x, we saw before, is v delta t. So x equals v bar delta t plus x 0. So let's see if it yields the right answer. Average velocity is plus 2, the time is 8, and the initial position is minus 4. So we end up with a position of 12 meters. It is positive, which means it's north. So the dog ends up 12 meters north of the house. If you notice, the area did not give us the position. The area gave us the displacement. So we can get the displacement, but to get the position, we need to factor in or add in the initial position. The initial position is a correction factor, which we have demonstrated on previous lessons on displacement graphing, displacement and position graphing. So